Hello everyone. In our last class we have discussed about the expression for Fermi energy level at absolute zero temperature, and we find out the expression was EF0 equal to h cross square by twice m 3 pi square n whole to the power 2/3. Now in today's class we would like to find out another very important parameter, which is the average kinetic energy of an electron, and it is denoted by E0 bar. From the definition of the average energy, we can write E0 bar equal to 1 by n 0 to infinity E dE, that is the density of energy states at E, and the Fermi function dE. And we know the characteristics of the Fermi function at absolute zero temperature is as follows: F equal to 1 for E less than EF0, that is in this energy range it is 1 and 0 elsewhere. So if we use these characteristics, then our E0 bar becomes 1 by n 0 to EF0 E, and we have placed the expression for D as C e to the power half, and Fermi function is 1 in this limit 0 to EF0, and the second part becomes 1 by n EF0 to infinity E C e to the power half, and Fermi function is 0. Therefore the second part will be 0, and we will get 1 by n C 2/5 e to the power 5 by 2 0, limit becomes 0 to EF0, and if we apply these limits we will get 2/5 C EF0 to the power 5 by 2 by n, and as we know from our previous class that n, that is the number of electrons or number of field energy states, as 2/3 of C EF0 to the power 3 by 2. So we will use this n here, and we will get the final expression for average kinetic energy of an electron is equal to 3/5 EF0, and this is also the total energy of the electron, because here we have considered our electrons are free particles. So the kinetic energy is the total energy of the electron, and the average kinetic energy of an electron is equal to 3/5 of Fermi energy level, and we can see that at absolute zero E0 is a constant. Now the same E0 could be expressed in terms of the atomic radius. That means if we consider the metals and it consists large number of atoms, and we can express the average kinetic energy of an electron in terms of the radius of these atoms. First we will consider the atoms are monovalent, that is each atom will provide a single electron as a free electrons inside the metal. Hence the volume of the atom is equal to 4/3 pi r cube, where r is the radius of a single atom. Let us consider that the volume of the metal is V. That means in 3D the volume of the metal is V, and this V volume contains n atoms, so therefore one atom can be occupied within the V by n volume. Since we have considered the monovalent crystal, that means number of atoms is equivalent to the number of free electrons. And as we know that n, small n, is equal to n by V, it is the electron concentration. So here we can write V by n equal to 1 by small n. Hence we can write this is the 4/3 pi r cube, which is the volume of a single atom. That means one atom can occupy that much volume, and since in monovalent crystal the number of atoms is equal to the number of electrons, so we can say that the electron, a single electron, can also occupy that much volume. So 4/3 pi r cube equal to 1 by n. Hence our expression E0 bar becomes 3/5 of EF0, and if we use the expression for EF0 what we have obtained in our last class, it is h cross square by 2m 3 pi square n whole to the power 2/3, and then by simplifying this one, 3/5 h cross square by 2m 3 pi square, and in place of n we will use this relation, therefore it becomes 3 by 4 pi r cube whole to the power 2/3. Therefore, the final expression for E0 in terms of the atomic radius becomes 3h cross square by 10 m 9 pi by 4 whole to the power 2/3 1 by r square. So this expression is for monovalent solid. But if we consider the polyvalent metal, then the electron concentration is replaced by n by z, where z is the valency of the metal, and then the E0 bar, that is the average kinetic energy of an electron, becomes 3h cross square by 10 m 9 pi z by 4 whole to the power 2/3 1 by r square, where we have used the radius of an atom is rs. Now we would like to find out the velocity of an electron. What will be the velocity? This is the another parameter. We would like to find out the velocity of an electron. We have the average energy of an electron in terms of the Fermi energy level. It is E0 bar is equal to 3/5 of EF0. If V0 bar is the average velocity of an electron, let us consider inside the metal the average velocity of an electron is V0 bar, then the kinetic energy of that electron is half m V0 bar square, and this kinetic energy is equivalent to the average energy of an electron, because we have considered the electrons are free particle. So the kinetic energy is the total energy, and there will be no potential energy for that electron. Therefore we can make these two terms equal, that is E0 bar is equal to half m V0 bar square, and by rearranging this equation we will get half m V0 bar square is equal to 3/5 of EF0. In place of E0 we have used this 3/5 of EF0. Therefore V0 bar square is equal to 6 by 5 m. M is the mass of the electron EF0. So if we use that EF0 is equal to 5 electron volt, which is the average Fermi energy level for metals at absolute zero temperature, which is 5 electron volt, and mass of the electron is 9.1 into 10 to the power minus 31 kg. And if we substitute these values in this expression, we will get V0 bar square is about 1.05 into 10 to the power 12 meter per second, and in CGS unit it is 1.05 into 10 to the power 14 centimeter per second, and it is near about 10 to the power 8 centimeter per second. So V0 bar is the average velocity of an electron at absolute zero temperature, and which is about 10 to the power 8 centimeter per second. Now we would like to compare this average velocity of an electron with the classical one. Classical theory says that the average energy of an electron at the Fermi level, which is about kBt, and it is 0.025 electron volt, and this V0 bar is near about 10 to the power 6 centimeter per second. So we can compare these two. Quantum mechanically we have obtained it is 10 to the power 8 centimeter per second, but classically it gives us 10 to the power 6 centimeter per second. So we can say that the velocity distribution is also altered drastically by the application of quantum mechanics. Now we would like to move for another parameter, that is we want to get the velocity of an electron at the Fermi level. In the previous one we have found out the average velocity of electrons, and these electrons are within the range of 0 to EF0. But right now we would like to find out the velocity of an electron, expression for the velocity of an electron if this electron is at the Fermi level EF0. Since we know that the velocity, we are denoting this velocity as Vf0, and the velocity can be expressed as momentum of the electron at the Fermi energy level divided by mass of the electron, and hence if we use this relation we will find Vf0 is equal to root over twice m Ef0, it is the momentum, divided by mass of the electron. Therefore Vf0 becomes root 2 by m, and we are using the expression for Ef0, which is h cross square by 2m 3 pi square n whole to the power 2/3 whole to the power half, and Vf0 equal to root over 2 by m h cross square by root 2m 3 pi square n whole to the power half whole to the power 1/3, and we will get the final expression for Vf0, which is h cross by m 3 pi square n whole to the power 1/3. And if we substitute the values of h cross m and small n, then we will find it is near about 10 to the power 8 centimeter per second for monovalent atoms. So it is the energy of an electron at the Fermi level, which is about 10 to the power 8 centimeter per second for monovalent atoms. Now we would like to find out what is the wavelength associated with the electron at the Fermi energy level. So for that we will use the de Broglie's relation, which is lambda f0 is equal to h by m Vf0, and it gives us it is near about 10 to the power 8 centimeter. So at the initial of our class we have discussed that the wavelength associated with an electron which is very large, which is 10 to the power 8 centimeter per second, and which explains why the mean free path of the electron inside the metal is so large. So from here we can find out the answer for that, because the lambda associated with the electron is 10 to the power 8 centimeter per second, and this lambda is for that electron which is at the Fermi level EF0. And since we know that this Fermi level is the highest energy level when the metal is at absolute zero temperature, so this wavelength associated with electrons is the minimum wavelength. So far we have discussed about the different parameters at absolute zero temperature. That means we have find out the expression for the Fermi energy level, we have find out the average energy, this is the average kinetic energy of the electron at absolute zero temperature, we have find out what is the average velocity or V0, which is the average velocity. We have also calculated the velocity of the electron at the Fermi energy level, what is the wavelength lambda f0 associated with the electron when these electrons are at the Fermi level. But all these parameters we have calculated at absolute zero temperature, that is T is equal to 0 Kelvin. In the next class we would like to know the effect of temperature on these parameters. So thank you for your kind attention.